get started with the afternoon. And we have one more talk in our session on control of neural circuits. And I think this will build nicely from the talk that we heard before lunch, sort of thinking about some of the clinical applications. And we have Jeff Moehlis who will talk about his research, sort of talking about some of the theory behind that and how we might control these things using control theory and banding.
All right, so thanks to the organizers for the invitation. Everyone can hear me okay? Okay, so this work was done roughly right about there at UCSB. And I'll just quickly go through this because Scott gave a very nice introduction to Parkinson's disease. I'll just mention it affects about 1 million people in the US alone, huge costs for treatment and lost productivity, the symptoms that he went through nicely. I'm going to consider this hypothesis that at least some of the symptoms are associated with pathological synchronization of the neural activity in the motor control region. And the different treatment options are drug treatment and deep brain stimulation. I'll be focused on the deep brain stimulation like he mentioned, where an electrode is implanted into like the subthalamic nucleus, and an electrical signal is injected into the brain tissue and almost magically makes some of these symptoms go away. Okay, so I'll show my favorite video. This one's from YouTube, so I think it can be recorded and everything. I didn't have anything to do with this particular individual. His name's Andrew Johnson from New Zealand. He got early onset Parkinson's disease. He also seems to have a bit of a sense of humor, so his blog is called youngandshaky.com. And I'll show this video here just to sort of set it up. So he has a pacemaker implanted. There's a device that can turn the pacemaker on and off. When it's on, it causes the electrical stimulus to occur. And what you'll see, he starts off with it on. He'll turn it off. You'll see what happens, and then he'll turn it back on. And just as a warning, I've shown this video many times before. Some people find it a little disturbing to see because it looks so unpleasant. So just a brief warning about that.
This is the Neurocontrol. And this cheeks them on. On, okay. Shaking too much. So it's almost an instantaneous reaction. I can control this. Shake some quality cocktails with the right. The left just looks like the royal wave. My voice is gone. It's harder for me to get words out and speak. I'm completely rigid, and if I try to stand up, I fall. If anyone thinks I'm faking this, I can't control the tremors and dyskinesia. The twisting in my neck is called dystonia, and it is really quite uncomfortable. So, as you can see, the tumours are getting much worse, and I'm in quite a bit of discomfort. And I'm about to drop the remote control, which will be fun because I'm going to turn the stuff back on. So, I think party time is over. Almost automatically. Power comes back on. Let's see. So, if anyone's considering DBS, I thoroughly recommend it. It's life-changing. Thanks.
Okay, so when I see videos like that, I'm still amazed. I mean, I've watched that dozens of times by now. It's still just amazing how almost instantly when he turns the DBS stimulus back on, the symptoms are alleviated. Now, the question is, how does it work? Okay, so Scott gave a nice discussion of different ideas of how it works. I'm going to be kind of exploring this synchronization, desynchronization hypothesis. And then I'll put on my engineering hat and ask the question, can we make it work better? Can we change the stimulus in some way in order to make it perform better? And typically, one of the ways to make it work better, it might not be just more effective, but also uses less power. So there's a battery in the pacemaker that runs out roughly every 2 years. Surgery has to be done to replace that battery. If you can make the battery last longer, less surgery, less potential for complications, and so on. Okay, and I'll be looking at models which involve neural oscillators. So this is actually the Hodgkin-Huxley equations for a particular value of the baseline current. We get periodic action potentials here. And I won't show you the equations. Steve showed those earlier. What I want to do, though, is discuss a reduction procedure where we start with the original, fairly nasty Hodgkin-Huxley type equations up here and reduce the system, the so-called phase reduction, so we get a very simple equation for the dynamics. So here's just a quick introduction. The phase reduction is based on something called isochrons. So if we have this system with a stable periodic orbit with period capital T, we define an isochron to be a set of initial conditions that share the same asymptotic convergence to the periodic orbit. We can view the isochron as a level set of a phase variable. So you take a state of your system, associate a phase with it, theta, and then if you parameterize these phase variables, the theta coordinate, in a convenient way, the dynamics are very simple. Just d theta dt is equal to a constant, 2 pi over the period. And this is true both on and off the periodic orbit. It's kind of a nonlinear polar coordinate change in some sense, where you're choosing your angular coordinate, your phase coordinate, to have very simple dynamics. Here's an illustration of isochrons. So the black curve is the stable periodic orbit. This is voltage. This is a gating variable. So this is a stable periodic orbit. The blue lines are isochrons, and these are equally spaced in phase, which means, well, if you look at the dot here, the trajectory moves more quickly through this part of the periodic orbit. That would correspond to the action potential. I'm starting with initial conditions on the same isochron. It's a stable periodic orbit, so the trajectories approach the periodic orbit, and they approach with the same phase, which means all 3 of those neurons would fire at the same time. This is just an illustration of so-called phase circle. So the dynamics here are very simple. You're just advancing at a constant speed, whereas here it looks like you're going more quickly through that part. And if I start with initial conditions on 3 different isochrons, all 3 trajectories will approach the stable periodic orbit, but they have different phases, so they fire at different times. Okay, so that's the notion of isochrons. And if we do a phase reduction of the equations with some perturbation, it turns out you get a very useful equation here. So if u was equal to 0, u is my control input, so you can think of that as something like the dBs input. If u is equal to 0, I just recover my d theta dt equals omega. But when u is included, I get this extra term. I have this function z, which is something called a phase response curve, which is the gradient of the phase here just with respect to the first component of x, because my perturbation is just coming into that component. This would correspond, say, to the voltage equation in the Hodgkin-Huxley equations, and that multiplies the input u. Okay, so this function z, as I mentioned, is called a phase response curve. If here I'm saying it really is the voltage component. So it's a gradient of the phase evaluated on the periodic orbit. You can think of it in terms of this limit here. So if I do an instantaneous change in voltage, V goes to V plus delta V, that kicks me to a different isochron. that changes the theta value. So I have a delta theta. If I take the ratio delta theta over delta V, limit as delta V goes to 0. That gives me the phase response curve. So you can think of this as capturing the effect of impulsive perturbations to the voltage. It would be like a delta function of current goes in, how much change do you get? And for the Hodgkin-Huxley equations, this is what the phase response curve looks like. You see sometimes it's negative, sometimes it's positive. And this tells us in some sense that timing is everything. So if I kick my periodic orbit when the phase is here, where the PRC is negative, that kicks me, let's say it's a positive delta V, that kicks me to a lower value of theta. It'd be a negative delta theta. Then my dynamics would just be d theta dt is equal to omega. It takes me longer to come back to where the neuron fires. So this actually makes the neuron take longer to fire an action potential. Whereas if I did the same exact kick at this phase, it advances the phase. Delta theta would be positive, and it makes the neuron fire more quickly than it would have had I not kicked it. So that starts to make us think, okay, maybe we can design some sort of control algorithms where, say, the timing of the kicks is important. We can change the timing of the action potentials based on those. One important thing to mention about this is if you can get a neuron in a petri dish, you can measure this experimentally also. Okay, so we've heard a lot about models, and there seems to be a consensus that all of our models are crap, right? None of them actually accurately describe our system. Well, that may be fine, because if we can experimentally measure this phase response curve and design control algorithms based on that phase response curve, we don't even need to know the model in some sense. So maybe that's overstating. But at any rate, that gives us a little hope. Yes? Yeah.
It's not obvious to me that it should converge. So, for example, if you need a positive voltage versus a negative voltage, if you have, it's not clear to me that it wouldn't be nonlinear, and you get basically different curves depending on what voltage in the
right. So mathematically, if you do have your model and so on, you do end up getting, what matters is, if I go back one slide, what matters is, just z times u. So if u is positive versus negative, it comes in the same way. Experimentally, it may be found that the PRC is different for, sort of kicks in different directions. But at least, based on the models and the theory of isochrons and so on, what comes in to this equation depends on if u is positive or negative. It just multiplies that PRC. We can talk more about that later if you want. Okay, so the first question that I posed was, how does DBS work? What is the mechanism? So I want to tell you a little bit about one idea that we had for how it works. So in DBS, you have these pulsatile periodic stimuli. So some strength S, some period tau. If I take a population of oscillators and subject them to that forcing with different strengths and different frequencies, you get an interesting so-called Arnold tongue type structure where, depending on what region of parameter space you're in, you might get one cluster or two clusters or three clusters or 4 or 5 clusters and so on. And by clusters, what I mean is that, say if I have 2 clusters, half of the neurons fire at some time and then the other half fire at a different time, really half a period later. If I have 3 clusters, you divide into 3 sets of neurons. And so instead of all the neurons firing at the same time, which would be sort of this idea of, if the neurons are too synchronized, you're in the Parkinsonian state, it seems that DBS may split things up into these clusters. Here's a representation of that. So here's a phase circle. Each dot corresponds to a neuron. These dots are actually moving around the circle, but we're strobing right before pulses come, just because it holds the clusters in the same place. So you see here, it looks like 3 clusters. I'm in that tongue there. Here's what one cluster looks like. There's noise in the system, so everything does get spread out a little bit. Here's a case of 3 clusters and so on. This is just averaging over the snapshots, looking at the average density over the snapshots. What we found, and at first, this was a bit of a surprise, when we're in, say, a 3-cluster state, there's roughly an equal population of neurons in each of these clusters. And we were able to understand that using Frobenius-Perron theory, and it kind of made us think that, okay, well, maybe in DBS, what's happening is when you tune your parameters, you tune the strength and the frequency, you get yourself in one of these tongues, and we call it clustered desynchronization. So it's not a full desynchronization, but all the neurons aren't firing at the same time. Say only a third of them are firing at the same time, and perhaps that's desynchronized enough that it can make some of the symptoms go away. Another thing related to clusters, Scott mentioned briefly coordinated reset. Here, instead of having a single probe, they have, say, 4 probes for the population of interest. This is just a measurement probe here. Essentially what they do is they inject the same signal into each of the probes, but the stimulus is delayed by, say, a quarter of a period between each of these. And what seems to be happening is subpopulations entrain to each of the electrodes, and they're out of phase with each other. So effectively, it's like you're getting, say, 4 different clusters in this case as well. And this is a protocol that seems to work well. And in fact, when you turn off the stimulation, the benefits seem to persist for some time afterwards. So that makes us think that there's some plasticity effects going on. That's a different story that I don't have time to tell you about today. But ultimately, these investigations led us to the following control objective. So basically the idea is maybe clustering is a good thing. Okay, the way DBS seems to be working right now is it leads to clustering. When you do coordinated reset, you get clustering. Maybe that should be our control objective. But instead of using multiple electrodes, let's try to use a single electrode that clusters using minimal power. The minimal power, again, is to sort of make the battery last longer. Okay, so I'll tell you a little bit about an algorithm we came up with for clustering. So I'm doing a very simplified model here. These results seem to persist when we introduce some heterogeneities and noise and so on. But let's start with if we have identical neurons that all receive the same input U, same input because we have a single electrode which is stimulating everything. If we order the phases of the neurons at t equals 0, it turns out when they're identical that ordering is maintained. So the neurons can't cross each other in phase. Yeah.
What do you mean by identical?
So they obey the same equations, they have the same frequency, they have the same phase response curve, and so on. Yeah. Okay, so suppose that we have here just 4 neurons, and we want to create 2 different clusters. Because of this ordering property, if we pair up these neurons like this and try to force both of them to be pi out of phase with each other, then you end up with this sort of 2-cluster state. Okay? Now, in reality, we have many more than 4 neurons. Here I'm showing just 10 neurons. Oh, sorry. But if you choose the same pairs as before, because the ordering is maintained, it sort of squeezes all these additional neurons into the places you want. So just by controlling these 2 pairs of neurons, we're able to form the 2 clusters for 10 neurons, or if we want, many more neurons. Okay. So if our goal is to split n neurons into k clusters, we define a state function according to this. It's kind of a messy formula, but the idea is we're forming k different pairs of neurons. For a given pair, we have this function here, which is equal to 0 when that pair is 2 pi over k out of phase. And it blows up to infinity when you approach a phase difference of 0 or 2 pi. Okay? And then we're summing over all the different pairs of neurons that we want. We form then a cost function where we're trying to minimize this. We want to minimize u squared. That would be the power which comes in due to the DBS stimulus. And we want to minimize the state function because, remember, each term was equal to 0 when it was at the desired spacing. Now, it turns out we can choose u so that dr dt is monotonic, so then we can sort of treat r as a time-like variable. And then if we look at the limit of this cost function as t goes to infinity, we can write it as an integral dr. And then we choose, it's sort of a greedy strategy, we choose u to instantaneously minimize that. So I'm skipping some of the math details. I'll just show you a movie here. So, is it going to play? Okay. So here, this is in terms of phase models. So I have each dot represents a neuron. This is the input that we're calculating. It looks a little bit like bang-bang control, but the limits are changing over time. This is the state function versus time. This is the cost. And what we're trying to do is create 4 clusters. Yeah, question?
Do the neurons connect to each other?
For this movie, they're not connected to each other, but the results do persist when we have weak coupling. So I don't have a movie for that. But the same sort of behavior does occur, as long as the coupling is relatively weak.
Excitatory or inhibitory can change this one.
Sorry, say again?
I mean, if they connect by excitatory connections or inhibitory, the results will be reversed.
So in this case, it's really a question of how strong the coupling is. Yeah. So the input can kind of overwhelm the coupling either way if it's weak enough. But so you can see that we do have these 4 different clusters. There's kind of an aliasing effect, but okay. You see that we are able to drive it to the 4 clusters using this input. Here, just to prove that it works, we apply it to kind of the full model. This is a Hodgkin-Huxley model. Here is voltage versus time. The neurons all start off kind of firing at the same time. We're trying to drive to 4 clusters. You'll see some spikiness. That's when we estimate the phase. It's not completely accurate, so you get some spikes here. But ultimately, very similar type of stimulus to before. Maybe I'll jump ahead a little bit if it lets me. I don't know if I can do it here. If we let this run, what we see is that the neurons are clustering here. You can kind of see it a little bit already. Things are color-coded, so like the blue ones, you see that there's 1, 2, 3, 4 clusters before they repeat again.
So the reason to believe that 4 clusters is better than uniform distribution?
Well, that's a good question. So here I'm showing some other desynchronization methods where we were looking for full desynchronization instead. And part of the reason why we explored the clustering was because those results I showed at the beginning, that the way DBS is presently done, it seems to lead to the clusters. So we think, maybe that is a good outcome. But we've also done several different control methods that try to completely desynchronize things, spread things out as much as possible. This we called chaotic desynchronization. It was an optimal control problem where the cost function is essentially the Lyapunov exponent between a pair of neurons, and we're trying to make that as large as possible so they spread out in phase as quickly as possible. We formulated it as an event-based control problem, so when the dots are red, the control is on. When they're blue, the control is off. So we're sort of monitoring something like a local field potential. If that's telling us that it's too synchronized, then we turn on the stimulus to desynchronize. If things are desynchronized enough, we leave the control off until coupling pulls them back together. We have to do it again. This method, optimal phase resetting, it's kind of inspired by Art Winfrey's phase resetting ideas. If that little green dot there is an unstable periodic orbit, if you look at the isochrons and follow them, they all kind of converge to that green dot. That's something we call a phaseless set. At that point, the dynamics are very sensitive to noise. Essentially, a small amount of noise can randomly kick you to different isochrons. And so we design a control input that takes us essentially to that green dot. It'll happen here. So you see they get pushed to the green dot, then the phase gets randomized, and so we can desynchronize that way as well. So there's several different tools. For the Hodgkin-Huxley equations, it turns out it takes less power to desynchronize using chaotic desynchronization versus optimal, but depending on your neuron model, you might get different results. And then, clustering is another possibility. Let me see how I'm doing. Okay. I'm almost done. I just wanted to tell you a little bit about some of our work on a more detailed model. So up to this point, I'm just considering a population of neurons, a single population, and trying to do something to it, make it clustered, make it desynchronized. But as Scott showed us, the reality is much more complicated than that. So you have STN neurons, GPE neurons, GPI neurons, cortical inputs, and so on. This is the Hahn-McIntyre model that was also studied by Abby Holtz and Tay Netoff. And when you look at this model, you get some interesting results. So the black line, so this is the power spectrum for the GPE neurons. The black line is the healthy situation. This is essentially due to the cortical input. But you see in the beta band, for the healthy patient, there's not such a prominent peak here, whereas the green line for Parkinson patient is much more prominent. So you have this enhanced beta activity. If you then do DBS stimulus to the STN and look at the power in the GPE, you find that it seems to knock that peak down. Okay, so this is maybe an alternative viewpoint. It's not obvious if that has to do with synchronization or not, but there's something about the DBS input when propagated to this other neural population seems to decrease the beta band. So we investigated that a little bit and came up with something we call phasic burst stimulation. So we start with essentially the same equation as before. Here, using a periodic unit pulse with period equal to the natural period of the system, you can say, well, if the initial phase was phi I, when we kick it, wait a period, and kick it, then phi I goes to phi I plus c phi I. If I consider another nearby neuron with some deviation epsilon I, then we kick it here. If I then look at how far the neurons are apart in phase after one kick, well, it's just the initial separation times this. And so if the derivative of the phase response curve is positive, that means that that phase difference is growing. And we can generalize this argument to multiple pulses. So essentially, I didn't show you the inputs for the optimal chaotic desynchronization. This is sort of a version of that. You could view this as like a Lyapunov exponent. When you kick it, it's separating things. And if you look at the phase response curve, you take the derivative where that's most positive, that's going to give you the most bang for your buck when you kick it. Okay, so when we, and I should mention for this work, it's essentially a generalization of the phase response curve to a population level phase response curve. But when we then look at this epsilon I plus 1 over epsilon I using a single pulse and a burst stimulus, which is basically just 3 pulses very rapidly, as a function of the phase at which we're stimulating, we find this sort of result. Okay, so this is essentially calculated from the PRC. And when we look at the change in the beta level activity relative to the gamma level activity, you see that when we're pulsing relative, theta equals 0 would be essentially when the population is firing. If we pulse here, we see that the beta level activity goes down quite a bit, but if we pulse at the wrong phase, it goes up. And you'll notice a nice similarity between what we're getting here from the phase response curves, where it's negative and then goes positive, and what we're getting here as well. So it seems, we're essentially choosing our pulses in order to desynchronize and in order to make things move apart in phase as much as possible. And that seems to have this effect that it decreases the beta band. So we're pushing down, which seems to be something good based on the studies, kind of going back to this plot. We're essentially pushing this peak downwards. Okay, so In conclusion, kind of returning to the clustering idea, it seems that DBS as presently implemented can lead to clusters. And based on that, we developed a low-power algorithm that uses a single input to drive to such a clustered state. I didn't have time to show you, but we applied this to other neural models. Really, all you need to know is the phase response curve of your neurons. They can be weakly coupled. You can add noise and so on. The algorithm seems robust, at least for sufficiently weak coupling and sufficiently small noise. Some other control methods, okay, just very briefly, I mentioned the chaotic desynchronization, optimal phase resetting, and phasic burst stimulation. I sort of view these as tools. There was a hammer analogy made earlier, okay, so we have 4 different hammers here, okay. Depending what your nail looks like, you might find one or another of the hammers to be more useful. But all of them lead to desynchronization in their own way. Okay, just to mention, I've been very fortunate to have a number of great collaborators. I bolded the students who were involved in this work. So my current student, Tim, is doing the clustering work. My former student, Dan, so he's doing the controlling to clusters. Dan did the work with the Arnold tongues. Ali did the work on the optimal phase resetting. Abby Holt from the University of Minnesota did the work on the phasic burst stimulation. And I should thank the NSF for funding. We're very happy to be able to do cool work here. So anyway, with that, I'd like to thank you for your attention.
So you have uncoupled, intrinsically oscillating neurons, and I don't know the details in the brain areas you're thinking about, but you're aware that ing and ping and other network-based mechanisms for generating oscillations. So if that were stochastic neurons individually at rest, but coupled in a way that leads to oscillations, what would that change for you?
Yeah, so that's a great question. It turns out you can generalize these phase reduction ideas to systems that have stable fixed points rather than stable periodic orbits. And you can define something similar to a phase response curve that we call an isostable response curve. We haven't done this yet, but I believe that these sorts of methods could be generalized to that type of situation as well. But yeah, the brain is a complicated place, right? And so this is a very idealized model where everything is periodically firing and everything's identical and so on. In reality, probably most of these neurons require noise to fire. I believe that the similar techniques could be applied in those cases. We just haven't really gone down that road yet. Okay.